Well, let's look at a well-posed problem. In the example I give above here, this is a small PC company, have this much capital, 12 millions, and limited labor supply, 100, and also limited floor space. So try to purchase 3 different machines to maximize the productivity. To make it easier for me to illustrate, I restricted the problem into 2D by assume the manager already made the decision, purchase 5 of the type C machine. So now you only have 2 choices, A and B. Going to find how many machine of type A you're going to purchase, how many type B to purchase, then you can maximize the productivity. Now the objective function need to add the productivity of the 5 C machine. That make a total of 50 to 80. You're going to do the calculation later on. And assume we purchase X1 of type A, X2 of type B machine, and those machines will make 990 of the computer boards per month, and this make extras per day. And type B make 900 boards per day, and then your total productivity per day is going to be 990x1, 900x2, plus 5,280. Then the first constraint is really the investment in $1 million. You start from 12 million, but the type C each cost 700,000. That 5 cost 35,000. Then total cost 3.5 million because of 700,000 times 5. And then you have 12 million minus 3.5 million. That's where you get this 8.5 million. And the type A machine cost 0.4 million per machine, and type B cost 0.6. So that's the financial constraint. The second equation is a little artificial flow constraint. Maybe you have to set this machine in the same manufacture shop, and that's give you the second equation. The third equation is the labor constraint. That's the labor constraint. You start with 100 operators, and the third type, C, takes 30 of labors. You have 70 left. And then to operate the first machine, you need 3 operators per day. And the second machine, you get 6 operators a day. So you got the 3 constraints. Now, compare what we learned in last lesson. See, those are all in equations. None of them are equation. As long as you don't exceed those resources, you're fine. And of course, the number of machines are all positive. That's another 2 constraint. Now, we can illustrate this in the graphics. That give you a clear illustration. What is the real problem? Let's identify line by line. The first equation is the money constraint. That will be the red line here, 8.5. And that's the first equation. It's a straight line down here on the top. That's the G1. And the second constraint is, you see the 70 here? That's the third one actually, G3, about the labor constraint. And the second one is here, G1, is the flow constraint. Each constraint corresponding to a straight line. That's why we call it linear programming. It's a linear equation. And then you add another two lines. That's obvious. And the x1 must be positive, and the x2 have to be positive. So these are the other two equations. So altogether, give you a so-called feasible domain, which I'm drawing right now. It is obvious like this smaller one. So that's the physical domain. And you have 4 of those extreme points, A, B, C, and D. I want you to pay attention. The G1 is outside of the physical domain, the feasible domain. So basically, that's an inactive constraint. What means inactive? Means this company have enough money. Money is not an issue. And the real issue now is the labor constraint, and that's the G3, and the flow constraint, that's the G1, and of course the other two are positive machines. Okay, so how do you find the solution? Now it's pretty obvious. All I need is find the point of A, B, C, and the D. They all have their coordinate. Then you plug in into the equation. I don't know what's going on here. You just keep backing. Okay, here you go. Now, to find the solution, all I need is find out the 4 extreme points. And those points happened in this A, which is the origin. B is the second point. C is the top corner point. You see, A is the origin, and the B is this point. You can see the y equals x2 equals 0, and the C is the corner point here, and the D is the point x1 equals 0. So we find those points. As the diagram shows, the constraint of the money is inactive because it's outside of the feasible domain. And then the constraint of the flow is active, and the constraint of the labor is active. That gives us the point C, which is giving the maximum solution. Well, you can also compare the A, B, and the D, and the plug into the F. You're going to find that the number is not as big. So automatically say, oh, C, which is x1 equal 10.458, you may be round off to 11, and the x2, 6.43, you can round out to 7 or 6, depends on you. And then your solution is purchase 11 of the type A machine and the 7 type B machine, that will maximize your productivity. So I think that should be clear enough when you have a few parameters. And also another visual way for you to visualize the solution is moving this line, the blue line, which is really the objective function, at the different levels. And you remember the coefficient is 990x1 and 900x2. You remember then the slope is around the -1, and that's the blue line. And if you move this blue line parallelly, that gives you the level. For example, in the first blue line, you get 525. In the second blue line, you get the 2000. But one constraint, your solution need to be inside of this physical domain. So if I move this blue line to this point here, let me move this. Like here, you can see that particular solution will maximize the height of this productivity. And that C is the unique point you have. So if you move anything in, of course, you're going to reduce the productivity. If you move out, it will be violate the constraint. So that C, obviously, is a solution when you move up and down of this blue line, which is the F function. So that gives you a kind of simple idea, hey, how we can solve it? All we need is find all the extreme points and then plug into the extreme points to compare which one's bigger. Looks like your same idea you learned in the calculus. How do you find the max and the minimum in an interval or in a box? Oh, you just plug in the critical points, plug into the boundary points, and you compare. And the real problem is when the constraint equation m and the variable n too big, is typically the m is bigger than n. You have more constraints than the variables. Your k is the total number of extreme points. And this total number of extreme points equals the combination to choose n points from the n equations. So each extreme point is really made by the choice of n from the n. So that number, if you learned any probability or combinatorics, you know it's a factorial of n divided by the n factorial n minus n. Let me be more specific. Look at the example. Assume you have 10 constraints. That's a small number in real world problem. Have n design variables equals 6. So what is the number of extreme point? That will be 10 factorial divided by 6 factorial. And then 10 minus 6 is 4 factorial. That will be 220. Basically, you need to solve 220 equations to find all those extreme points. That's really practical. It's not a practical way to do it.